So welcome for today's session. So in the last tutorial we were talking about the independence, few conditions of independence. So what does that independence means? So it means if you take any matrix, so whether it's a matrix A or any other matrix, when do we say that this matrix is independent? So why do we need this independence? Because this independence will define in the next coming subsection that when we talk about the basis. So basis is one which forms the basics of the vectors so that we can span the other vectors or we can span the entire space. So that basis to find out, we need to identify which are the independent columns. So the one of the method of defining the linear independence is that when we have ax equal to 0, when we are talking about in a null space, when ax is equal to 0, so for the columns to be independent, the only solution is that this x should be equal to 0. So then we say that it is a linearly independent columns, and no other columns of ax of columns gives the 0 vector. So that is what it means. So we have taken two examples of the diagram where we had discussed about the vector v, where we had said that we have three vectors, say v1, v2, v3, v1, v2, v3, and all these vectors are in the different plane. They are independent and they are in different plane, but we cannot find the combinations of all these. So there is no combination at all. So to get the combination is only that we have to multiply all these vectors by 0 so that we can get it to a common point. So that is 0 vector space. So then the other thing is that we have one more vector, that is w1, w2 and w3. They are all in the same plane, but these are all dependent vectors. These are not independent vectors. So and we have taken a couple of examples of the vectors, that 1 0 0 1, these are all considered to be independent vectors. And we had taken one previous example. I'll just quickly revise on the previous example, then we will continue with our today's session. So in last tutorial we had taken one example here, so that is 1 0 3 1 0 3 2 1 5 1 0 3. So now we have to check whether this is independent or not. So how do we define whether it is independent or not? So that depends on the rank of the matrix, and this rank of the matrix should be equal to n. So now what is the value of n here? So there are three columns, so it's actually a 3 cross 3 matrix. So there is a 3 cross 3 matrix. It means it has a 3 rows and 3 columns. So here for the linear independence, the rank of the matrix should be equal to the number of columns. So here the number of column is 3, but is it the rank of the matrix is 3? So that is what we have checked yesterday. So when we go for the row elimination process, so then finally we got that with the echelon row reduction method, we got the final reduced matrix in the form that is 1 0 3 0 1 minus 1 0 0 0. So now if you see, there is 1 0 row here, and we have only two columns which has the pivots. So here we have only three columns which have the pivot, and the rank of the matrix is equal to, since there are only two pivots, the rank of the matrix is equal to 2. So is this a independent matrix? So that is the question here. Is this an independent matrix? No, this is not an independent matrix. This is a dependent matrix. So if you write here, so this is the dependent matrix. Why? Because the rank of the matrix is not equal to the column of the matrix. If the rank of the matrix is equal to the column of the matrix, it means we have the three pivots in this matrix. Then we can say that these vectors are linearly independent, and they fill the space, and they fill the entire space. So that is what it means. So there is a third definition as well for this. So the column of A are independent exactly when the rank is n, when the rank is r is equal to n. We had written this definition in the previous tutorial also, in the last definition. And there are n pivots and no free variables. If you look into this example, we have two pivots, we have two pivot columns, that is the first and second column is the pivot column. Whereas if you look into the third column is a free column here. Whereas the definition of linear independency, it says there should not be any free variables or free columns. So then only x equal to 0 in the null space. So that is the definition. So apart from that, let us take one more a simple example here. So for example, we have say 7 columns. We have 7 columns and with 5 components. So we have 5 components. It means we have 5 rows. So it means it is a 5 cross 7 matrix. It's a 5 cross 7 matrix. It means it's a short and wide matrix. It means it has 7 columns and 5. Can this be a independent, linearly independent? No. Why? Because uh, it should be r power. Now the for a 7 vectors with r power 5 are independent. So this we will come to this r power 5. What is this? So r power 5. So here when we are talking about the column space, so then the dimension of the matrix depends on the value of m. So that is why we write this as r power 5. So now for this matrix to be uh, independent, they're supposed to have 7 pivots, but since we have only 5 columns, for example 1 0 1 2 3, so if you write like this, it means we have only 5 rows. So even if you go with the elimination matrix, we left out with 2 rows, we doesn't have the pivots, so it will become the free columns. So in such case, this cannot be an independent column, so this will become a dependent a matrix, because the columns, the other columns which are there, it might be combination of the other columns, so it is not an independent case, it's a dependent case. So that is how you can understand. So that's what it is given. So there might be 5 pivots but 2 columns, because for this matrix to be independent, they're supposed to have the rank of the matrix, that is R, should be equal to n. So the value of n here, it is 7. The rank should also be 7, but in this case it is not at all possible to get rank equal to 7, because we have 5 rows. So in 5 rows, but max we can get only 5 pivots. So this cannot be, in this case it is not, R is not equal to n, so it means it is not a independent, linearly independent column vector or column space. So it's a dependent matrix. So there are certain definitions that we will follow here. So that is, for example, when we say here, so any set of n vectors, so we have n column vectors in r power m, so that I'll write later, so must be linearly, so these are the conditions, must be linearly dependent if n is greater than m. So it means that for r power m, so when we are talking about the column space, then the dimension of the matrix is depends on r power n, means the number of rows. So any set of n vectors, it means, so if you take the previous example here, there is 5 cross 7 matrix. If the columns are 7 vectors in r power 5, must be linearly dependent if the value of m is greater than m. So that's what we told. It is not independent, it's a linearly dependent case where n is greater than m. Whereas if we say in some case, if n is sorry for that, if n is less than or equal to m, there might be possibility that it might be an independent or dependent. That depends again on the number of r pivot columns in the matrix. Now let's talk about the vectors that span a subspace. So let me save this page here. So now we will talk about the vectors that span a subspace. Span a subspace in the sense, so here we are talking about the vectors which fills the entire subspace. We'll start with the columns by taking an example here with say we have the vectors v1, v2 and dash dash up to vn vectors. So the subspace was filled out by including all the combinations. So now we will multiply with the scalar value, that is x1, that is unknowns, that is x1 into v1 plus, then we'll add all these columns vectors, that is x2 into v2 plus etc, and then we'll consider that xn into vn. Then the column space consists of all combinations of ax of columns. So that is what means a column space consists of a combination of ax of columns. So now let's see the definition of this span here. So a set of vectors spans a space if their linear combination fills this space. So that is what this vector spans definition. So let me write here on the definition. A set of vectors. So consider that we have a set of vectors and that spans a space. It means it will fill the space if their linear combination fill the space, if the linear combination fill the space. So now let us look into a few columns, a few examples of the column that spans the column space. They might be dependent or they might be independent as well. So if we talk about these kind of examples here, so in the first example we have vector v1 which is 1 0, and there is another vector v2 which is 0 1. So these are actually an independent vectors here, so that spans. So now this is, if you put this in the matrix, so then it is a 2 cross 2 matrix, and then the dimension of the matrix is r square, because if you put them into matrix form like this 1 0 0 1, then it is perfectly in a identity matrix, and we have the 2 pivots and 2 rows, therefore these are independent, and these are the linearly independent um, vectors, and it fills the entire two-dimensional space. So let's take one more example here. So v1 is equal to, we have say 1 0, and we have v2 is equal to this v2, we have 0 1, yeah, it's fine, but we have one more vector, that is v3 is equal to, that is 4 and 7. So this also fills the span, but the dimension of the matrix is, it's a two-dimension matrix, because the row, the number of rows here, if you put into matrix, it is only 2 rows, but still this will also fills the space. Whereas when we talk about the one more case here, so I'll write here. So when we take the w1 is equal to 1 0, sorry 1 1, and w2 is equal to -1 -1, then the only span is in r square is a line. So we will get only a straight line here, and it fills that line, because here 1 and 1, it comes in the first quadrant. If you draw a two-dimensional plane here, so we get a point here and we get a point here, so it means we'll get the span, means it will going to fill the line span. So that is what this means in the combination of functions. Okay, so now let us talk about something about the row space, and the definition goes like this. Now for the row space, the dimension is defined by the number of columns. It is reverse. For column space, the dimension of the matrix is defined by a number of rows, that is r power m, and for row space, the matrix, the subspace or the dimension is defined as r power n. So now let us write the definition of this row space here. So okay, so the row space definition, the row space of matrix is the subspace of R power n spanned by the rows. And so how do we define that row space? So we will not define the row space in terms of rows. What we will do is that we will take these rows to columns by performing the transpose of these matrix. So the row space of A is column of A transpose. So I'll write that transpose. So column of A transpose, then it is the column space of A transpose. So here the missing terms I'll write it. So this is R power n here. So this is R power n, and this is a transpose of A transpose. So let us look into definition once again. So the row space of matrix is the subspace of R power n. So now when we talk about the row space, then it depends on the subspace of the number of columns. So the dimension is now R power n spanned by rows. And now we will not see them in terms of rows, we will bring them to the column form by performing the transpose of a matrix. So now it has come to the column space, but it is not just A, it is the A transpose of it. So that is what it means. Now for example, let's take a small example here. Now if A has say the values of 1 4 2 7 3 5. So now here we have to describe the column space and the row space. So the column space is that and the column space is R power 3. So the column space is defined by a plane in R power 3 and spanned by 2 columns of A, and the row space is defined by 3 rows and width in a 2-dimensional plane, that is R square. So if we take the A transpose of this, then what we get is so the A transpose is, that is, we get 1 2 3 and 4 7 5. So this is the transpose of this. Okay, so the rows are in the R power. So let's quickly take the few points here. So the rows are in R power n spanning the row space, and columns are in R power m spanning the column space. So this is very important point here when we talked about the vector space and subspaces. So let me write that point here. So the rows are in R power n spanning the, this spans the row space, this spans the row space, and the columns in R power m, it's spanning in the column space. Okay, so these are the important points. So we'll just summarize this before going to the next topic.